Hello, and welcome to a lecture on the cylindrical parabolic antenna. In this lecture, we'll do uniform geometrical theory of diffraction analysis. My name is Steve Ellingson. First, a reminder about what cylindrical reflectors are. A cylindrical reflector is parabolic in one plane, and it is the cylindrical extrusion in the other. So it looks something like this. Here's a parabolic cross-section. And then here is the extrusion to make it cylindrical. So it looks something like this. Now I've probably talked in detail about this type of antenna in a previous lecture. The beam in the plane of the parabola is typically relatively wide, and the beam in the other dimension is relatively narrow. So we refer to the type of beam that this type of antenna generates as being a fan beam. The applications of cylindrical reflectors include air surveillance radar and radio astronomy. And another reason to take a look at this type of antenna is because it can be viewed as a two-dimensional prototype for a three-dimensional paraboloidal reflector. This facilitates insight that might be difficult to achieve in the more complex 3D case. So in other words, one way to understand the way a three-dimensional paraboloidal circular reflector antenna might work is to first consider a cylindrical reflector that has comparable dimensions and try to understand that before introducing the additional complexity of going to 3 dimensions. Here's an overview of this lecture. First, the problem statement. Then we'll work through the construction of the UTD solution. I'll show you the results. Then I'll show you how this compares to physical optics. I have probably presented a physical optics solution to this problem in a previous lecture. I will not go through the derivation of that result, but I'll simply compare that result to the UTD solution that we obtain here. And then a few concluding remarks. So here's the problem statement. This is the example shown in section 16.6 of Stutzman and Thiel. That is the 2013 version of that book. The reflector, again, is in 2 dimensions. The dimension of the reflector, the overall diameter, is 10 wavelengths. The F over D is 1/2. We're using a cosine squared feed model, in which the feed is located at the origin of the coordinate system, with x and y being the plane in which we're considering this problem. Setting up the problem this way allows us to use all the variables and coordinate systems that we've established for 3-dimensional paraboloidal reflector antenna design in previous lectures. So for example, here's theta f, z sub f goes in this direction, this is the focus, also known as the focal point, and so on. Again, we're assuming focus-fed, axisymmetric with a cosine squared feed model. And note here that because we're in 2 dimensions, this is a cylindrical wave, not a spherical wave. And the big difference is, of course, that the electric field drops off as 1 over the square root of distance, as opposed to just 1 over distance. And this is the kind of field that you would expect from a line feed. Line feeds produce cylindrical waves. So this is a 2-dimensional problem, but it's a very good approximation to an electrically long reflector. In other words, this would be a good approximation for a reflector which looks like this, where this dimension D is much less than this dimension. Okay, so when we construct a UTD solution, we build it up from parts. One part is the geometrical optics field, and the geometrical optics field itself has parts. So first, let's consider the geometrical optics incident field. So here is the feed right here. Here is the reflector. And then this curve is showing the cosine squared pattern. And what we see is that part of the incident field strikes the reflector. Some other spills over, and we've identified this as spillover regions, which will produce a geometrical optics incident field in the far field. But there will be no other angular regions other than these that are shaded here for which we will get a direct contribution from the feed. We define the pattern to be 0 back here, and we're blocked by the dish over here. So the geometrical optics incident field, which we'll name E super I, is by definition here the feed pattern, but evaluated only in the region where there's spillover. Again, this is the field that is radiated directly from the feed that makes it into the far field. If we plot that, we can do that. Here is magnitude of the electric field. Here is phi in degrees measured from the x-axis here, and plus x is the direction in which we expect maximum gain. And if we plot that, we get this simple pattern like this. We get a taper that looks like this because of the cosine squared pattern. And then we hit the instant shadow boundary. And the instant shadow boundary is right here. It's lit on this side, and it's dark on this side. So what we see is when we hit the incident shadow boundary, we suddenly go to 0 because now we're on the reflector. So that's the geo incident field in the far field. The geo-reflected field is in one sense very simple, but in another sense there is a subtlety here that you have to be careful about. Now the geo-reflected field is a field that comes from the feed, strikes the reflector, and then is collimated and travels in the desired direction. And we get one of those contributions for each point on the reflector. So in fact, there are an infinite number of geo rays all traveling in this general direction. And when we go to the far field, the way this looks is that we have an infinite number of rays passing through a single pattern angle. In other words, at phi equals 0, we get an infinite number of rays. At any other value of phi, we get 0 rays. Obviously, an infinite number of rays, which is a caustic, by the way, implies an infinite field. So we really can't have that. So the reflected field, ironically, is 0. Now this may seem counterintuitive. After all, this is a reflector antenna. However, this is as it must be. A limitation of GEO is that it predicts these types of caustics in certain situations. So we know that the UTD total field is going to be bogus in this direction. Now we can consider diffraction from the upper edge. So our feed is here. We imagine a ray coming up here and striking the upper edge. We know that in UTD, the result depends on the positions of the incident reflected shadow boundaries. We have an incident shadow boundary up here. This is dark. This is lit. We have a reflected shadow boundary here. This is lit, and this is dark. Right? Again, referring to the reflected field. And we know that we must have diffraction radiating from that discontinuity. And we're going to call that E super D sub 1, 1 referring to the upper edge. Now, something to consider here is that there is this region down here where diffraction, in the sense that we're considering here, is shadowed by the reflector. In other words, a diffracted ray which comes off this way does not make it into the far field in this direction. Rather, it would be reflected by the reflector. So anything in this region is shadowed in terms of this particular mechanism, and instead should produce a spray of diffraction which goes off in this direction. Now, we're not going to consider that. And it's going to turn out to be a reasonable thing to do because this turns out to be a relatively weak mechanism. But it is there at some level, and in a more complete solution than what we're going to do here, you might need to include these contributions. So when we compute a diffraction from the upper edge, we have to define a 0 face and an end face. The 0 face of the edge is always the one that most directly faces the source. So the lit face is here. So this is the 0 face. The end face is the other face. Phi super I, again, the value that we use in the diffraction coefficient looks like this. The angle to the diffracted ray, as described in the expressions for the diffraction coefficient, is this angle here. It's a little bit clumsy notation-wise. we use that variable phi for that angle. Of course, phi is also the angle relative to the x-axis. So you'll have to forgive that double use of variables. The distance from here to here is s sub 1. And we're going to do one other thing. We're going to model the rim as a half plane tangent to the surface. And that's a reasonable approximation if the radius of curvature of the surface is large. Now, this is a 1/2 f over d 10 wavelength reflector. So this dimension's 10 lambda. And so this curvature is very, very large relative to a wavelength. So this is going to turn out to be a pretty good approximation to model the diffraction as if it's coming from a straight edge. Again, we could improve the result by actually taking into account the curvature, and we already have the expressions required to do that. But here we're going to try to keep it as simple as possible, and we'll make this approximation, and we'll see it really doesn't make that much of a difference in this particular case. The field diffracted from the upper edge, we can write this way. It's plus b sub naught super I, this unit vector that we used in the ray-fixed coordinate system for diffraction, the soft diffraction coefficient, and then a cylindrical wave. And then you can work out from the definitions of these coordinate systems that in this case, this unit vector is just plus z hat. Obviously, it has to either be plus or minus z hat, but you should make sure that you can see that this is in the plus direction. Okay, here's the field diffracted from the upper edge. We see along the reflection shadow boundary, which is coincident with the direction of maximum directivity, we see a relatively large value, and then it decreases, and then it comes up, and then it peaks at the incident shadow boundary, and then it comes back down again. And again, this is what we expect. We expect that diffraction is maximum at the geometrical optics shadow boundaries. One reason that is that the diffraction must mitigate or smooth the discontinuity in the geometrical optics fields. Well, we have an incident field and we have a diffraction from the upper edge, and we can add those two things now. So if we go ahead and add those two things, this is what we get. It's a small evolution from what I showed in the previous slide. Now we can do diffraction from the lower edge. And the considerations are all the same. We have an incident shadow boundary. We have a reflection shadow boundary. We have a region where the diffraction is shadowed. And we'll assume that that isn't important. And it isn't compared to other things that are going on here. But for a completely rigorous solution, we would need to add those at some point. Here's the geometry. Once again, we define or identify the zero face and the end face. We assume we can model the edge as being a straight edge because the curvature of the reflector here is relatively large. Again, that might be a refinement that we make to the solution later. And we'll define the distance from the lower edge to the field point to be S2. And the field diffracted by the lower edge to be E sub 2 super D. So that electric field is given by this expression. Looks very similar, of course, to the field diffracted from the upper edge. However, the unit vector here that's relevant is now minus z hat. So again, you should make sure that you can see how that comes about. Here is the UTD field diffracted from the lower edge. Again, maximum at the reflection shadow boundary, and then it just gradually decreases. There's a region here where it's shadowed by the reflector, so it goes to 0 exactly, as indicated here. Now we have three contributions. We have the incident field, we have fields diffracted from the upper and lower edge. Now we can add all those things up together, and now what we see is that out here in front of the reflector, we see those two diffracted rays interfering with each other. And then we see some more interference back here in this region, and so we're starting to make modifications to the total field that make it look more and more like what we actually expect to see. So here's the exact same plot, but now in dB, because this is the way patterns are traditionally depicted. I've indicated here again the reflection shadow boundary and the incident shadow boundary. Here's the region in which spillover is important. That is this region here, where the incident field, that is a field from the source, is non-zero and yet doesn't strike the reflector. Over here, we see fringing of the two diffraction points. So that's these two things going in and out of phase with each other as we move an angle back and forth. And then over here, we see a side lobe pattern because the diffraction points here are going in and out of phase with each other behind the reflector. It's worth noting here that we have some glitches remaining. For example, right here at 90 degrees, we have a discontinuity. It's small, but it's significant at the 1 or 2 dB level. This turns out to be double diffraction. So this is the problem that there's a ray that strikes here and then strikes here. That's 2 diffractions, and then it scatters. So that's what this glitch is. There's also a glitch back here. I believe that glitch is due to neglecting the curvature of the reflector surface. But again, it's relatively small. It's on the order of 1 or 2 dB, and in a region where we typically wouldn't care that much about the details. Although this could probably be cleaned up. And the first thing I would do here is I would recalculate the diffraction coefficients, including the curvature, not just assuming it's simply a straight edge. Now we can consider regions of validity. With these 3 mechanisms included, what we see is that we get kind of what we expect back here. And I will tell you that this is a pretty good solution for what's going back here, even taking into account these glitches. Again, the glitches could be cleaned up. It would be considerable extra work, and all it would do is just smooth out these results. Nevertheless, this whole region here is, to a good engineering approximation, valid. However, here we know this is garbage. And the reason we know it's garbage is, for example, it's predicting a null as opposed to a peak in the direction of maximum directivity. And that's simply because we cannot properly represent the reflected field that's culminated by the reflector. Again, because we have this caustic of rays in the far field. UTD and geometrical optics simply cannot do that part of the problem correctly. So you should expect that the main lobe and the first few side lobes are going to be bogus when you do UTD on this type of problem. Worth comparing the result here to physical optics. So here I'm showing you the exact same thing, but now with the physical optics result shown as a dashed line. So interestingly, what you see is, and what you should know already, is that physical optics does a great job for the main lobe and a great job for the first few side lobes. But once you get away from the specular region, physical optics performs poorly. And specifically, you see it does something very strange in the region behind the reflector, which cannot be physically valid. That field back there is very small, as is correctly predicted by UTD. So what do you do here? Well, the way these types of problems are typically reconciled is that you go ahead and you use physical optics for this region, and you go ahead and you use UTD for this region. In other words, you use the 2 methods in the regions which are valid, and then to stitch the 2 solutions together, you either pick a point somewhere where you stop using one and start using the other, or in other methods you might do some weighting between the 2 methods. So you weight physical optics more heavily here and less heavily here, and UTD vice versa. But if you're doing weighting or stitching together of solutions, the results are typically not that much different. The key idea here is simply to know that physical optics is the way to go here, and UTD is the way to go here. And when I say physical optics, by the way, you could just as easily be GOAI, geometrical optics aperture integration, or some other method that properly does the main lobe. So, concluding remarks. Physical optics and UTD nicely complement each other. Each is valid in the regions where the other performs poorly, and we're lucky for that. Physical optics is the way to go for the main lobe and the first few side lobes. UTD is the way to go for far side lobes and behind the reflector. Remaining glitches in the UTD solution, and we've seen some, can be resolved by including higher order, that is, multiple scattering mechanisms. So, for example, we saw here that we could eliminate a glitch by including a double diffraction term, a term in which we diffract from one edge and then diffract from another edge and then radiate. We also saw a case in which we could probably do better by including the curvature of the surface, which we neglected. Now, I noted that UTD cannot properly do the main lobe. It was able to do the back lobe in this case, but in 3 dimensions, UTD fails for the back lobe as well. And the reason is, in a 3-dimensional reflector, we have this axis that runs through the reflector, and UTD predicts an infinite number of rays at each point along that axis. So in 3 dimensions, UTD also fails for the back lobe. The 2-dimensional case, it worked out okay because there is no back lobe caustic in 2 dimensions, because there's only just 2 diffracted rays. In 3 dimensions, there is an infinite number of diffracted rays along that axis. And finally, you might ask, well, what's the pattern in the narrow plane? In other words, we've been considering exclusively this plane. What about the other plane? Well, there you can use aperture theory. This thing is just a line source. So to a good approximation, you could just apply the theory of line sources, or more generally aperture theory, to come up with a pretty good guess. For example, if this was a uniform magnitude current source, or at least could be modeled that way, you'd know you'd get a sync pattern in the far field, and you would know the half-power beamwidth of that sync pattern and the side lobe levels. So this is a relatively simple problem compared to the problem of the pattern in the plane of the parabolic cross-section. This concludes this lecture on the cylindrical parabolic antenna UTD analysis.